In this video, we're going to talk about the mean value theorem and what it gives us, and also Rolle's theorem. We're going to start out with Rolle's theorem. So for Rolle's theorem to happen, it has to be a continuous function over some closed interval, and it must be differentiable on the open interval a to b. Now, the reason we do that is so that we don't have to worry about the endpoints. So we notice that the function that we start out with is a closed interval including the endpoints, but we just needed to be differentiable on the inside, the interior of it. And with Rolle's theorem, not only does it have to be continuous and differentiable on that interval from a to b, that my output for a and my output for b must be the same. If that happens, then somewhere in there I have some value within that interval a to b in which my derivative is equal to 0. So here's 3 examples in which my Rolle's theorem applies, that my output for a and my output for b are the same. So I'm guaranteed this point c in which my derivative is equal to 0. Here's my a and here's my b. My output at f of a and f of b are the same, and this is my c value in which that's true. Here's another example in which my outputs f of a and f of b are the same. In this case, I end up with 2 values of c in which my derivative is equal to 0. So my derivative being equal to 0 doesn't have to be just a singular number. It could be multiple places this could happen. So if we were asked to determine whether or not Rolle's theorem applies to each one of these, and if so, find the points that we're guaranteed to have. The first thing I need to do is determine whether or not f of my left is equal to f of my right. So for example A, I'm going to do f of my left, which is 0. So that is the sine of 2 times 0, which is the sine of 0, which does equal 0. Then I have to do the other side, so my b part, f of pi over 2, is equal to the sine of 2 times pi over 2, which is equal to the sine of pi, which also equals 0. So the fact that it has the left side equals the right side is confirmed. The second thing that I have to confirm is that it's continuous. Well, because it's a sine wave, and the sine of any angle theta is continuous on its domain. In fact, its domain is from negative infinity to infinity. So the continuity is confirmed. The third thing that has to happen is that the derivative must exist. Well, the sine of theta, the derivative of d theta, is equal to the cosine of theta times theta prime. So the cosine of theta, provided of course theta is a number that is a real number and I don't have to worry about imaginary numbers, that is also going to be in existence in the interval, in our case a to b, but our case it is from 0 to pi over 2. So everything is satisfied in this, so let's go ahead and find the c value, the value in which my derivative is equal to 0. So I do f prime of x is equal to the cosine of my angle multiplied by the derivative of my angle. So I have the cosine of 2x is equal to 0 because I need to have this set equal to 0 to solve. Divide both sides by 0 and I get the cosine of 2x is equal to 0. That means my angle is equal to whatever angles in which I equal 0 for cosine. Well, the only place that cosine is equal to 0 is on multiples of pi over 2 plus pi k. So when I'm straight up or straight down. Now I'm going to divide everything by 2, and I get x is equal to pi over 4 plus pi over 2k. So I need to find the values in which this is equal to, that's going to give me 0. So I have to stay within that interval from 0 to pi over 2. So the only place this is going to happen is when k equals 0. I'm going to get an output of pi over 4. So my answer here is when x is equal to pi over 4, I'm going to get a derivative that's equal to 0. Let's take a look at b. So the first thing is that I have to ensure that f of a equals f of b. So I put in -1 into my function. So 1 minus the absolute value of -1. So this is going to give me 1 minus 1, which is 0. And I'm going to do f of 1. So I have 1 minus the absolute value of 1, which is 1 minus 1, which is 0. So these two are equal, so that part is satisfied. The second part is I have to have continuity. So my function, f of x, is equal to 1 minus the absolute value of x. There's no places in the interval from -1 to 1, so on the interval from -1 to 1, there's no place in which that function is not defined or which we have to pick up our pencil as we draw it from left to right, so it is continuous. The last thing I have to check is whether or not the derivative exists. Well, on the interval from -1 to 1, this function, f of x, is equal to 1 minus the absolute value of x, looks something like this. So that's what my function looks like. So we know whenever I have a corner, in this case right there at 0, that it is not differentiable. So it is not differentiable on the interval from -1 to 1. So we can't apply Rolle's theorem to this. Looking at C, for C, I'm going to go through the same process as I'm going to make sure that f of -4 is equal to f of 2. So f of -4 is equal to -4 cubed minus 2 times -4 squared minus 8 multiplied by -4. So this is going to give me -64. And then I have minus 16 times 2 is -32. -32. And then minus is a plus. So this is positive 32. So my answer when I put a -4 is -64. Now I have to check it for 2. So I'm going to put 2 in there. And I have 2 cubed minus 2 times 2 squared minus 8 times 2. So I get 8 minus 16. This is going to give me -16. These are not the same. So right out of the gate, I know that Rolle's theorem is not going to apply to this particular polynomial on the interval from -4 to 2. So it may apply in a different interval, but for this interval from the required -4 to 2, it does not apply. Let's look at our next one, which is the mean value theorem. The mean value theorem says that it has to be continuous over the closed interval, so that's similar to the Rolle's theorem. It has to be differentiable on the open interval, also similar to Rolle's theorem. And then there exists at least one point such that the derivative of my point is equal to the slope between the endpoints. Now, Rolle's theorem is a specialized version of mean value theorem. Rolle's theorem, I wanted my f of a and my f of b to be 0, or excuse me, my f of a to an f of b to equal each other. That means the difference would be 0. The mean value theorem is generically, and Rolle's theorem is a special one. So what that tells us then, and here's an example pictorially, that here's my f of a, here's my f of b, here's the slope or the secant line between them, that there must be two places, or at least one place. In this example, I have two places, at least one place in which I have tangent lines that are parallel to that secant line. So if I have to determine whether or not the mean value theorem applies, I have the same criteria. I have the criteria that it has to be differentiable and it has to be continuous. In this case, it doesn't necessarily have to have f of a equal f of b, so that's one part I don't have to check. But I do have to check for continuity, and I do have to make sure that it's differentiable on that interval. So looking for differentiable and continuity, so continuous on the interval from 0 to pi over 4. So because this is a sine graph from 0 to pi over 4, the 3, all that does is increase the amplitude, and the 2, all that does is change the period. So the sine itself is continuous on the real numbers. The other thing I have to check is to make sure that f prime exists on that interval from 0 to pi over 4. And again, it's a sine wave, so its derivative is going to be a cosine wave. So this is obviously going to be continuous on there. So that because the mean value theorem applies, what I have to do is I do have to find the slope of the secant. To find the slope of the secant, the first thing I have to do is put in my endpoints. So I have 3 times the sine of 0. For my previous example, I know the sine of 0 is 0, so that's going to be 0. And I'm going to do f of pi over 4, which is going to be 3 times the sine of 2 and then pi over 4. And again, for my previous example, this equals 0. For this example, I am just really right back to Rolle's theorem, which is I have my f of a and my f of b be the same. So if I were to find the slope of the secant, because these are the same, the slope of the secant is going to be equal to my outputs divided by my inputs. So 0 minus pi over 4. This one just gives me 0, so I don't have to do anything like setting it equal to. This next couple of examples, that may not be true. So all I have to do then is say, okay, I need to find my derivative f prime of x. F prime of x is going to be 3 cosine 2x multiplied by the derivative of my angle. So I have 6, the cosine of 2x has to equal 0, because that is the slope of my secant, which in this case happens to be 0. Divide both sides by 0, and this is exactly where we were before. So 2x is equal to pi over 2 plus pi k, dividing everything by 2, pi is equal to pi over, x is equal to pi over 4 plus pi over 2k. When k equals 0, that's the only answer we get, so x has to be pi over 4, just like my previous example. Now, let's take a look at my next example. I have to check for continuity. Is my function ln of 2x continuous on the interval from 1 to e? Well, my logarithmic function is continuous in general from 0 non-inclusive up to infinity, because that's the domain. All this 2 does to my graph is do a horizontal shrink. So it's still going to be continuous on the interval from 0 to infinity. So it's definitely going to be continuous on the interval from 1 to e. So that is satisfied. The second thing I have to check for is whether or not the function exists on that interval. Well, since my derivative, since my function is continuous, and it's a smooth curve, so there's no kinks anywhere, that is also going to have the satisfaction of the derivative being existing on that interval from 1 to e. So now I go ahead and find f of 1. So f of 1 is the natural log of 2 times 1, so I'm just going to write that as a natural log of 2. And then f of e is going to be equal to the natural log of 2 times e. I'm going to use the laws of logs to break this apart. So the natural log of 2 plus the natural log of e, because multiplication is going on between them, I break them apart with addition. So now I'm just going to go over here and use the mean value theorem that states that the slope of my secant, which is f of b minus f of a over b minus a, must be equal to some f prime of c. So I'm going to find the slope of the secant, and that will give me the opportunity to find what c is. So I have the natural log of 2 plus the natural log of e minus the natural log of 2 all over e minus 1. But the natural log of 2 minus the natural log of e, well, these 2's cancel themselves out. The natural log of 2's cancel themselves out. The natural log of e is just 1. So what I have is 1 over e minus 1. So I'm going to find the derivative, f prime of x. It's going to be 1 over 2x multiplied by the derivative of 2x, which is just 2. So this is equal to 1 over x. So this is equal to 1 over x. So this is equal to 1 over x. Solving for x, my x is equal to e minus 1. This is the value in the interval from 1 to e in which, when I take the derivative, the tangent line is equal to the slope of the secant by the mean value theorem. Let's go ahead and take a look at the next example. So for this example, I have to ensure that it is continuous on the interval from 1 to 3. Well, my function f of x is equal to x minus 1 or plus 1 over x. The only place in which I have a discontinuity is when x is equal to 0. So when x is equal to 0, I have a discontinuity. 0 is not in an interval, so I have continuity. The next thing I have to do is make sure that f prime exists on the interval from 0. I have 0 on my brain. 1 to 3. So it is continuous on the interval from 1 to 3 because my function f of x is equal to x plus 1 over x. This is a rational function, and on its domain, rational functions are both smooth and continuous, so that is satisfied. Now what I have to do is I have to find f of my left side, so f of 1, which is 1 plus 1 over 1, which gives me 2. And then I have to find f of 3, which is 3 plus 1 over 3, which is 3 1/3. So now I'm going to find the slope of the secant, which is going to be equal to f of b minus f of a all over but b minus a. So this is going to be equal to 3 1/3. I'm going to write that as 10 over 3 minus 2 divided by 3 minus 1. So I'm just going to multiply everything by 3 to clear my fraction. In my numerator, I'm going to get 10 minus 6. In my denominator, I'm going to get 3 times 2. My numerator gives me 4, and my denominator gives me 6. So I have 2 over 3. I'm going to find the derivative of my function f prime of x. This is going to be 1 minus x raised to the negative 2. So I have 1 minus 1 over x squared is equal to 2/3. So I'm going to multiply everything by x squared. So x squared minus 1. Oh, let's multiply everything by x squared and then 3. So I can get rid of my fraction. So when I do that, I'm going to get 3x squared minus 3 is going to be equal to 2x squared. I'm going to add 3 to both sides and subtract off x squared from both sides. So I get x squared is equal to 3. X is equal to plus and minus the square root of 3. The only one that is in the interval from 1 to 3 is the x is equal to the positive square root of 3. So that's how we apply the mean value theorem. And if I were to take the derivative of my function and evaluate at the square root of 3, I should get the exact same answer as if I would have done the evaluation at the left side and the right side and found the slope between those 2 points. So in these examples, I'm chasing whether or not we have continuity and whether or not we have its derivative. So our first example here, I have to look for continuous on the interval from -1 to 1. Well, this is definitely continuous on the interval from -1 to 1, but it is most definitely not differentiable. That's the second piece, is does f prime exist on the interval from -1 to 1? And if I were to graph this function, what this function looks like is the absolute value function moved over to a positive 1/2 is where the turning point is. And so that there is a corner, so it doesn't exist. My next equation is from f of x is equal to 1 over x squared, so I have to check for continuity. So the first thing I always do is check for continuity. And my continuity from -1 to 1 doesn't happen because this x cannot equal 0. So we're not continuous on the interval, so I stop. My next function is, again, I'm looking for continuity between -1 to 1 on that interval. Well, it is continuous. There's no place in which the absolute value of x is not, and then the square root of that is not undefined, because if I take the square root of -1 and absolute value of it, that just gives me 1. So I don't have to worry about negative numbers. So from -1 to 1, it is continuous. Then I have to ensure that this exists on -1 to 1. Well, if I were to graph this thing, what ends up happening is I have this graph that looks like this. I have the square root on this side, and I have the square root on this side, and it is defined, it is continuous, but you can see right there, the derivative doesn't exist at 0. So I can't apply the mean value theorem, or Rolle's theorem for that matter, on either one of these two. Or this one, this example. So none of these examples will I'll be able to apply the mean value theorem because they're either not continuous on the interval, or the derivative doesn't exist on the interval. What we get from this is that these two breakdowns from our theorems, mean value theorem, is that if it's differentiable on some interval I, then there has to be some place in which a derivative equals 0. If it equals 0 on the entire thing, then we end up with a constant. So if my derivative is equal to 0 on that entire interval, then I know that I must have had a constant. So I must have had something like f of x, say, equal to 5. The other thing I get is that if it's differentiable on some interval, then, and if my derivatives are equal to each other, then my functions are just a constant apart. So as an example, if I have f of x is equal to x squared plus 1, my derivative is equal to 2x. But if I had g of x is equal to x squared, my derivative of my function, g of x, not f prime, g prime of x is equal to 2x. Now these two are equal, and you can see that they are a constant apart. The last thing we get from this is the intervals of increasing and decreasing. So if we have a continuous function that is on the closed interval and it is differentiable on the open interval, then if f prime of x is greater than 0 in this region, I am increasing. If my derivative is greater than 0. If my derivative is less than 0, then I am decreasing. And again, if it is greater than 0, then I'm increasing. So I can find my intervals of increasing and decreasing now. Let's take a look at an example. So let's go over here and take a look at this example. We want to consider this function f of x is equal to the natural log of x over x squared. There are two important numbers, a, which is on the left side, and b, which are critical or they're outside of the domain. So let's figure out whether or not they're inside the domain or if they're the critical value. And when we're talking about critical values, we're talking about what we learned in our previous sections, the points of the derivatives when the derivatives equal 0. So the first thing we want to do is do the derivative. So f of x, well, let's do this in black instead of yellow. F of x is equal to the natural log of x over x squared. And so the derivative f prime of x is equal to, and I'm going to do this as the product rule. I'm going to rewrite this as the natural log of x multiplied by x raised to the negative 2, so I can do the product rule. So the natural log of x derivative is 1 over x prime, and then multiplied by x raised to the negative 2, and then plus the derivative of x raised to the negative 2, which is negative 2x raised to the negative 3 multiplied by the natural log of x. So what I'm doing is I'm doing in the product rule, this is u, this is v, where u is equal to the natural log of x, u prime is equal to 1 over x. V is equal to x raised to the negative 2, v prime is equal to negative 2x raised to the negative 3. So this is u prime, this is v prime, this is u, just as a reminder of what I'm doing. So cleaning this up a little bit algebraically is I have 1 over x to the third minus the natural log of x over 2 the natural log of x over x to the third. So I can just write this as 1 minus 2 the natural log of x over x cubed. Now I'm going to go ahead and set this equal to 0. So I have 1 minus 2 the natural log of x over x cubed is equal to 0, because again I'm trying to figure out where my critical points are. So I'm going to go ahead and multiply both sides by x cubed, and I get 1 minus 2 the natural log of x is equal to 0. Going back to what I learned in pre-calc 1 is I'm going to move the 1 to the other side and divide by 2. So I have the natural log of x is equal to 1/2. And I'm going to turn this into its equivalent exponential form. So e to the 1/2 is equal to x. And so that is my x value. And that's in the domain, so because it's not equal to 0. So if I look back at my function, the natural log of x over x squared, here's my original function. I have two restrictions that I have to think about, which restriction on the bottom, so that can't, or the denominator, which can't be 0. But then again, I can't take the natural log of a negative number or 0, so I actually only have one restriction. The domain of this function is from 0, non-inclusive, to infinity, and e raised to the 1/2 is in that domain, 0 to infinity. So that is my one critical point. If I were to go graph this, so let's go to Desmos and do a quick graph. All right, so let's go back over here to these examples. We want to find, without actually finding the derivatives, which of the following functions have the same derivatives. By this point, we know that these two will have the same derivative because we have discovered that when we take the derivative of the natural log of x, whether it is a natural log of x or some constant times x, it would be the same. So dx, the natural log of x, will give me the same derivative if I do dx of the natural log of 2x. Because what ends up happening is when I do the derivatives of each one of those, and I do the derivative of 2x, that's 2, which means that those two will end up being the same. Same thing is true here, is all that constant does is just is a multiplier. And we know from our previous here, this is that they're going to have the same derivatives but with a constant between them. In this case, the constant is inside there. So if we take this one further and we find a function whose derivative f prime of x is equal to 1, that means we've done some derivative, d dx, of some function that when I get done, I end up with x plus 1. Well, the only way I can get 1 is if I would have started with x. The only way I can get x when I do the derivative is I had to have started out with x squared. But there's no 2 in front of that, so that must have had 1/2. So the function I had to have started is 1/2 x squared plus x. And that's going to be one of my functions. However, any function with a constant is still going to give me the same derivative. So my answer is f of x is equal to 1/2 x squared plus x plus c. And what this is doing is starting to set us up for doing integration. So we want to show the equation y is equal to x cubed plus 3x squared plus 16 has exactly one root. Now, it is a degree 3 polynomial. That means I'm guaranteed to cross the x-axis once and up to 3 times. But they're asking me to find that it has exactly one root, and then what is it? So the first thing I'm going to do is find the derivative of y prime. Y prime is equal to 3x squared plus 6x. Set this derivative equal to 0 to determine where I'm going to have turning points. In other words, where my derivative, or where my graph is changing from increasing and decreasing, my maxima or minima. So I'm going to factor out a 3x, leaving me x plus 6 is equal to 0. So when x is equal to 0 and when x is equal to -6, not -6, that should be, my factoring skills are a little slow today, that should be 2. So x plus 2. So when x is equal to 0 and x is equal to -2, this is where I have maxima or minima. So I'm going to go ahead and determine by the sign chart what's happening on each one of those. So when I put in my sign chart 3x and x plus 2, my sign chart will include -2 and 0. So I'm going to choose something on the left side of -2, so I'm going to choose, say, -3. So this is negative and this is negative. That means this region is positive. That means we are increasing on this region. I'm going to choose something between -2 and 0, so I'll choose -1. This is negative, this is positive, so in this region I am decreasing. So that tells me these two combined together tells me that this must be a local maxima. And now I'm going to choose something on the right side of 0, so let's choose 10. That's positive and that's positive. So that's positive, so I'm increasing. So that means that on this region, because this is increasing, from going from decreasing to increasing, that this must be a local minimum. So I know at those two places I've got a local minimum and a local maximum. So I'm going to determine by the intermediate value theorem, which is pre-calculus 1, whether or not there's a 0 between those. So I'm going to do f of 0. And I put in f of 0, I get positive 16. I'm going to get f of -2. When I put in -2, I'm going to get -8 plus 3 times positive 4 plus 16. So I have 12. So -8 plus 12 is -4, so this is 20. By the intermediate value theorem, it states that it's indeterminate. I cannot guarantee a 0 between those two, maxima and minima. All right, so then I also kick back to pre-calc 1, and I use René Descartes' rule of sign. So using Descartes' rule of sign, it says that if the sign changes between the terms, here, as the sign changes between terms, that's how many positive real roots I'll get. Well, I don't have any positive real roots because the sign doesn't change. Again, using Descartes' rule of sign, if I plug in a negative x, so y is equal to, it becomes negative x cubed plus 3x squared plus 16. I'm checking for a sign change between terms. It only happens one time. So by Descartes' rule of sign says I am guaranteed one negative real zero. So all the rest of my zeros, all the rest of my roots will be imaginary or complex. So Descartes says, look, I only have one real one, so let's find it. Again, I'm going to go kick back to what I learned in Pre-Calc 1, and I'm going to list out the positive rational zero, so that is the P over Q. P over Q is positive and negative 1, 2, 4, and 16. Oh, I need 8 in there too. 8 and 16. And I can get rid of all the positives because Descartes says I'm only going to have one negative and no positives. So I'm going to either use f of negative 1, so I'm going to either use the factor remainder theorem, or I'm going to use synthetic division to determine where one of these, if one of these, is equal to 0. Now I know one of these has to equal 0 because if I look at my original polynomial here, I look at this polynomial right here, I don't see any rational numbers here. I don't see the square root of 7 or the square root of 12 or anything like that. So I know it has to be one of these, and it's just a matter of finding one of these. So I put in negative 1, and I end up with negative 1 plus 3. Let me do that in black. So I end up with, let me see. Here we go. I end up with negative 1 plus 3 plus 16. This doesn't equal 0. Put in negative 2, so I end up with negative 8 plus, and we know from our previous one what this is going to equal, negative 8 plus 3 times 4 plus 16. This doesn't equal 0, so then I put in negative 4. I put in negative 4, so I get negative 64 plus 3 times 16 plus 16. It gives me the 0 that I was looking for. So the 0 I have is x is equal to negative 4. So to answer this, there is my answer. All right, last example, and then there's some questions for you to ponder. This last example says a state patrol officer saw a car starting from rest at a highway on-ramp. She radioed an officer 30 miles along the highway. When the car reached the location 30 minutes later, it was clocked at going 60 miles an hour. Can the patrol officer conclude the driver has exceeded the speed limit? And the answer is yes. And the reason that is go look at the mean value theorem. So by the mean value theorem, somewhere along there, I must have had my function f of t is equal to the rate of the car. I must have been going more than 60 to have a speed limit of 60 if I'm 30 miles away.